In this video, we're going to talk about why assessing eccentric deceleration ability matters, look at some data, and end with some case study examples. So first, let's just get into a little bit more about why this matters. We talked about this before, but the idea that injuries happen in these transition zones, right? Landing from a jump, changing direction, the sudden change of direction. This is where, classic like ACL injuries. Think about the NFL football right now. They're having ACL injuries. It seems like every single weekend, 5 to 6 people are going down. And, it's because these movements, right? They're high energy events. Eccentric movement abilities are different than concentric movement abilities, right? Different control of force, right, by our systems. And all of this together demands that we evaluate this, both the non-injured athletes, after you're coming back from injury, and certainly from the standpoint of fine-tuning our training. The time frame of these injuries, less than 50 milliseconds. They happen extremely quickly, which is why we need to attend to this with our programming and why we need to attend to this in how we test and evaluate our athletes. So I'm going to spend a lot of time today in this video talking about alpine ski racing, which is a unique sport, right? Alpine ski racers are exposed to lots of eccentric loading. The potential energy of the hill brings them down, and they basically absorb energy on the way down. But these athletes are among the best athletes out there, right? Everyone knows Bodie Miller, and others have actually won competitions, sort of the best all-around athletes. I can tell you that these are truly great athletes to study when it comes to physical performance. But let's just take a look at the kiss of death for alpine skiers. Such a high prevalence of ACL injury. Roughly probably 5 skiers per every 100 per season get an ACL injury, and a high fraction of them go on to suffer an ACL re-injury. Now, what you're going to see here are the kinematics on the left on the screen obtained from an ACL injury event, not connected to the video that you're going to see, but the video is actually also showing an ACL injury event as well. And so we're going to look at what's happening in this ACL injury event, and we're going to use this to start to inform our decision making around why assessing eccentric deceleration ability is so important for injuries. All right, so what we see is the ACL injury event is happening right there. You see the ski pop off the snow. It's a rapid load, and you can see him being forced into flexion. And indeed, when we look at the kinematic analysis from the athlete skier, or the skier in a study actually suffering an ACL injury, what we see is during the injury period, a massive change in knee flexion. So we're talking about knee flexion angle going from 25 degrees of knee flexion to almost 65 degrees of knee flexion in 60 milliseconds. And this is also associated with knee valgus loading and knee tibial internal rotation loading. And all together, what you see generally is there's external energy acting on the body, and this is forcing the body into a position where the ACL injury happens. And you might just call that an eccentric deceleration event. That's why we need to be strong and evaluate our athletes in terms of their eccentric deceleration abilities. And that's what we're going to focus on now. But first, let's take a look at some data. So here's an example of 2 athletes. They both are at 7.5 months post-surgery after an ACL reconstruction. And they are both at this stage in the game contemplating possibly a return to snow. And I want to just take a second to highlight in on the different counter movement jump profiles you see between athlete on the left and athlete on the right. And the first thing to notice is looking through that eccentric deceleration phase. And indeed, when we look at the athlete, the young development level athlete, kind of looks like something like this maybe, as we actually map out her curve. And then our senior elite athlete, again, also coming back after ACL injury, her curve looks something more like that. Now, what do we see in this particular image is we see a couple things. Number one, athlete number 1 shown over here does not want to unload, right? Do you see this? She doesn't want to unload, and that is an indication of, potentially, fear, guarding, but eccentric movement abilities is also about your ability to unload, right? It's not just putting on the brakes. So that's number 1. She's not unloading very well. Number 2 is we see that there's something happening in that early transition, that early braking point where she's putting on the brakes to reverse her downward acceleration. And we also see overall that there's really not a substantial peak for that true transition point from her eccentric deceleration phase to her concentric movement phase. If we look at the athlete, however, on the right-hand side, again, same time point, we notice number one, huge unloading potential, no issue there. She almost goes down to zero force. And look at the nice shape of the peak vertical ground reaction force there, which is corresponding roughly to the endpoint of her eccentric deceleration phase. So don't forget, it's also unloading, right? Athlete number one is not unloading, the braking phase is attenuated, and altogether, this starts to shape our understanding about being able to assess these eccentric deceleration abilities. Looking now, the athlete that you saw on the right-hand side of the screen in the last video, this is her profile taken at 4.5 months and 7.5 months post-surgery. We've already been through this, but you can see actually a different jump strategy, right, for the injured limb at 4.5 months, and then by 7.5 months, it's not only that she's recovered in terms of her symmetry, but the shape of the force time curve has also recovered. And what we see at that time point one is the shape that looks something like this. It's not only that her asymmetries are high, but she doesn't have that characteristic shape in the eccentric deceleration phase that we normally associate with skiers, and in this case, good jumpers in general. So this gives us a sense that her asymmetries are there, yes, but there's something distinct happening in the eccentric deceleration phase that deserves our attention and something we need to attend to. All right, let's look at some data. That's the beautiful thing about our environment. We've got tens of thousands of vertical jumps that we've been able to obtain on athletes over time, and we're able to use this data to build some normative data sets. We're able to plot out the concentric asymmetries and the eccentric asymmetries in the deceleration phase. We're able to compare between our non-injured group and our ACL injured athletes. And all together, this is what we obtain, which is showing some normative data when we look at vertical jump asymmetries between ACL injured athletes and non-injured controls across various phases of jumping. And this starts to inform a little bit about our understanding about what we might expect. And what you see in panel A is the counter movement jump eccentric deceleration phase. You'll notice that there's actually a bit of variability there, right? Comparatively, if we think about the control group compared to the ACL injured group, and we actually look at the panel B, which is our concentric movement phase, we actually see there's quite a bit of variability in the asymmetries in the eccentric deceleration phase of the counter movement jump. The high majority of them are contained between plus and minus 10%. But we're going to talk about why there are some elevated asymmetries and what that might mean from the area of sport injury. So you might be asking some asymmetry, wanting some normative data. Here's some normative data looking at the median asymmetry, the min, the max, giving you a whole range of various descriptive measures about what we might see. So the median asymmetry for the eccentric deceleration phase of the counter movement jump for our non-injured controls, you can see is 2.1%, but there is quite a bit of variability there in terms of what we might see. Okay, so that gives us a sense, right? We've got some normative data, we've got an idea of what we're looking at, but let's start to apply this into the real world. And let's start with an example here of a classic Achilles tendinopathy presented in an elite athlete. You can see on the top panel, that's the counter movement jump eccentric deceleration asymmetry. And you can sort of see this low grade asymmetry from the start of the timeline until about the midpoint, where really asymmetries start to creep up into the red zone, which is higher than 15%. And we're basing that off of our normative data. So what this is coinciding with is actually an Achilles tendinopathy. And you can see how slow and steady increase in asymmetries over the time course of his particular this particular case study, which is indicating that something is happening to the system, particularly through this eccentric deceleration phase. Because if we look at the concentric movement phase, there's very little to note about in terms of anything notable relative to changes that might be of interest. So here's the first point, is that when we talk about how many trials do we need to have to evaluate, let's say, eccentric deceleration asymmetries to know that something's happening in a non-injured athlete, the first thing that we may want to return to is how much data do we need to establish a movement pattern. And what some of the studies will suggest is that you need a minimum of 5 testing sessions to establish what a given movement pattern is. This has been established more in wearable training data, where we're obtaining these signals using IMU technology, but we might be able to surmise the same thing here. So you can see that creep up in his eccentric deceleration asymmetry as we have the onset of his Achilles tendinopathy. Another example here too, looking at an ACL injured athlete, is a male elite alpine ski racer returning after an ACL MCL injury. And here what we have is some pre-injury and post-injury data as he's coming back to sport. And I always say it's avoiding these regrettable cases. This video here is unrelated, but it's one of our skiers who suffers a contralateral knee injury at about 14 months post-surgery. And I have to say, this is really the impetus behind a lot of the work. So we're trying to get better data points to be able to help inform our decision-making about return to sport after injury. So we're gonna focus on this guy though. He's our athlete for the case study, and we're gonna talk about what you see in blue, pre-injury data, red as he's returning to sport, and then green, back in the green zone and back ready to get back to snow. Now, the point of this case study, and this is building off of our previous previous videos, where we talked about the fact that concentric movement abilities and eccentric movement abilities are not necessarily the same thing. And here what we're seeing, first of all, on the panel that you see on the screen is his concentric asymmetries. You'll see in blue, that's pre-injury. Red is post-injury recovery. Orange is where he goes back on snow, and then green is at that sort of post 1 year mark after his injury. And you can kind of see when you take a look at his recovery and his interlimb asymmetry, you can see that that recovery over time is actually not occurring in a linear fashion. The recovery in his concentric movement asymmetry is actually happening sort of more in a hyperbolic fashion. Now, nevertheless, when he got to that stage at 7.5 months post-surgery, the decision was made for him to get back to snow. So clearly what we're seeing there is that he's below that 15% threshold. There was other factors involved, but this is where the determination was made for him to return to snow. But now let's take a look at his eccentric deceleration asymmetry, because we don't see a hyperbolic relationship. What we see is actually a linear relationship over time as he makes his recovery back to that 7.5 month time point for his return to snow. But here's what happens, and here's what's interesting. After being back on snow, a large amount of eccentric loading is obviously involved in alpine ski racing. What we observe as he comes back, and we measure him at that time point as he exits that first on snow return to snow, is we actually see an increase in his eccentric deceleration asymmetry. Essentially, he's had a small regression, right? Not a significant amount, but a small regression. And I can tell you as well that in other sports, thinking about field sports, right, where I've had the opportunity to look at some data from professional athletes, I can tell you that that return to sport, where they're back on the field of play, playing the game, not thinking about rehab, is oftentimes where regressions happen, because now they're loading back to the way they used to load when they were in the earlier phases of the rehab, right? They're starting to load more through the non-injured side, and there's a training effect that goes along with that. You start to develop more strength, more rate of force development capacity on the injured limb because of the fact of, you're moving differently. So this is an example of where we could use this sort of tracking concentric versus eccentric movement abilities in an athlete coming back after ACL injury. And kind of an important point here just to mention is when we look at that 18-month post-injury time point, I just wanted to point out that just because asymmetries are okay, don't forget that you can always have 2 weak legs, right? You can be symmetrical but not very strong. And indeed, what we see in a lot of our data is that really 18 to 24 months is minimum to restore these neuromuscular capacities after injury. And importantly, let's take a look at his eccentric braking impulse. Eccentric deceleration impulse is really what this is. And you can see that from pre-injury to post 1 year, you can see that we still have not really recovered that full eccentric strength capacity by the 18-month time point. Okay, just wanted to spend a little bit of time talking about visualizing the eccentric deceleration phase, especially for the point of knowledge translation. And I talked about these beautiful force displacement loops, right, where we calculate change in force divided by the change in displacement throughout that eccentric deceleration phase. And these force displacement loops paint a beautiful picture of the eccentric deceleration phase. And this is something actually in the Naraxin software, the new MR3, that you can actually do is you can plot out these loops really easily. So you may remember it's like reading like a clock, and we can see those loops, and they're work loops, right? So they actually tell us about jump performance too. And we can also plot the left versus the right and see a nice picture of recovery after surgery. So let's just take a couple of examples where we're now characterizing eccentric deceleration ability by looking at these force displacement loops, these work loops, in an athlete coming back after injury. So here we can see the athlete early on in recovery. There's a marked difference between left and right, both in the eccentric deceleration phase and in the concentric phase of the jump. We start to watch the recovery happen though over time. And what we start to notice is the recovery of that eccentric deceleration phase and ultimately the recovery of the concentric propulsion phase as they recover strength and power throughout the rehabilitation process. And what I can tell you is that visualizing the jump in this fashion using these work loops and being able to characterize that eccentric deceleration phase is actually a really powerful tool for communicating knowledge across to an athlete or a coach about where the deficiencies may linger after injury. Our second case study that I want to look at is less of a case study. It's maybe a small pilot, but we had 66 athletes who were tested at baseline from wrestling, alpine skiing, soccer, rugby. They 49 females, 17 males, and they performed 5 counter movement jumps and 5 squat jumps at baseline. And we conducted injury surveillance throughout the 4 months of training subsequent to the baseline test. And here's what we want to focus on. Again, injuries that happened were all around the knee. We had an ACL injury, we had a patellar dislocation, that's the bone, a lateral collateral injury, and a medial collateral ligament injury, all associated with non-contact injury mechanisms. When we broke down asymmetries and we looked at squat jumping and counter movement jumping, only one movement phase was really telling, and that was the eccentric deceleration phase. What we found for the non-injured controls was on average the interlimb asymmetry was about just around a couple of percent. But when we looked at the non-injured group, we looked at the injured group, this is the group that went on to suffer a knee injury, we saw that the average asymmetry for that group was more on the order of 10%. And when we break this down and we start to think about decision making, what we start to see when we look at this, we look at these eccentric deceleration asymmetries, is we see that if we had used a threshold of 20% as a cutoff, right, to make some decisions about the athletes, to potentially say, hey, we might need to engage in some other training or some different types of neuromuscular control training or eccentric resistance exercise. We might have been able to identify these athletes as only the athletes who went on to suffer an injury, and not inadvertently also included some athletes in the non-injured group who in fact were not of issue in that 4-month study period. So again, from a thresholding standpoint, this idea of an interlimb asymmetry in the eccentric deceleration phase more than 20%, or consistent eccentric deceleration asymmetries that don't vary above and below that center black line, meaning that the right and the left leg are, session by session, jump by jump, also sharing some load in braking. These are potentially some red flags that we can use to flag athletes who might need our attention. I'm not saying we're predicting injury here. What I'm saying is we're identifying potentially trainable deficits that we can mitigate. If we knew they were there, we could do something about it. And that's where I want to end this little case study presentation, is talking about these deficits. Are they trainable? So case study 3, male alpine skier, no suspected history of injury, and this is really just a preventative effort. And what we're looking at are his eccentric deceleration asymmetries in the counter movement jump. And importantly, what we're going to show are some stable and high eccentric deceleration asymmetries that were reversible through training. So here is a profile of our non-injured skiers and our injured skiers. And you might be wondering, why was the variability so high in eccentric deceleration asymmetries in that non-injured group and the normative data that we showed? And the reason is that some of these athletes are actually contained in this group, right? So some of these athletes, and one that we're going to see here right now. I also want to talk just briefly about where some study around this stuff can actually be quite informative. So what we did is we undertook a study where we looked at 12 development level skiers, 12 elite skiers, and 12 ACL reconstructed skiers. All the ACL reconstructed skiers were far along and back to sport, and we used 5 counter movement jumps to look at limb stiffness. And it was really interesting to note limb stiffness left to right shown on the screen for the ACL group and the control group. You can see there's no real difference left to right, like their lines are going up and some lines are flat and some lines are going down, suggesting that there's no real pattern. What we observed with our young development level skiers, systematic right side dominance. And this was an unexpected finding. We went back and looked at the data and really tried to understand this, but for some reason in this group of young alpine skiers, they were all right side dominant in terms of this eccentric deceleration phase. In this case, what we were measuring was limb stiffness. Also, when we broke down the net eccentric impulse for the eccentric deceleration phase compared to the concentric movement phase, we found no difference in propulsive ability between the development level and the elite athletes. However, where we did see a small but statistically significant difference was in the eccentric deceleration impulse. So this idea of measuring eccentric deceleration impulse is important. And to give you some normative data, 1.6 to 1.9 Newton seconds per kilo, this is where we're starting to get into a good level of eccentric deceleration impulse. When you see values below 1.5, so 1, 1.2, 1.3, these are generally quite low values of eccentric deceleration impulse. And really what it's telling us is the capacity to reverse that downward acceleration of the body center of mass. But it's an n=1 game. And I want to get back to this picture. This is our picture of our development level athletes and our national team athletes, and it's going to explain why we have such a big range in our normative data for the non-injured controls. And it kind of comes down to athletes like this. This is an athlete that's non-injured. It's got no suspected history of injury, no ACL injury, nothing. And what we're looking at are extremely high eccentric deceleration asymmetries, more than 20%, right, with normal concentric movement phase asymmetries. And I want to talk a little bit about how we got the red dots back into the green zone, which occurred through an intervention after observing these high eccentric deceleration asymmetries. So this was a relatively stable finding over time. In fact, look here, there's at least 10 data points over time suggesting that this isn't just a one-off. It's not just one testing session where this guy's eccentric deceleration asymmetries were high. In fact, they were consistently high, test over test over test over test over test. When we intervened, as you can see, the bottom panel is showing eccentric deceleration asymmetry and the top panel concentric asymmetries. You can see concentric asymmetries are all in the green zone, nothing notable there, but look at the change over time after we were able to intervene. So here's our 3 baseline measures. Remember, there's like 5 or 6 other measures that are exactly like this. So this individual has eccentric deceleration asymmetry, but no present of concentric movement asymmetry. But through some interventions, we were able to get him back into the green zone. And I'm going to talk in the next video about how we do this, but what it comes down to is it comes down to really assessing the constraints that are available to, the constraints that are shaping our movement strategies. And you may remember this is Newell's model, right? We're going to talk about our internal constraints, the task constraints, which might be the cues we give, the environmental constraints, and together this is going to shape our eccentric movement abilities, which are the skills, and our eccentric strength capacities, the ability to make force fast throughout this phase and range of motion. And we're going to talk a little bit more about how we can shape this through training in the next video.